Welcome back. In today's lecture, we're going to talk about scheduling. Specifically, we're going to focus on CPU scheduling. That is, scheduling processes or threads to CPU cores. Scheduling, though, has broad implications. We'll see in a couple lectures how some of these same scheduling algorithms can be used for devices like storage and networking. But it also has applications all over user space. Whenever you have resources that are contended upon, we have to make scheduling decisions. So here we can see an example of a bunch of jobs that are being assigned to a bunch of processors. We can have one or more CPUs that are processing these different jobs. These jobs could be processes, they could be threads, they could be individual executions of some task. How we place and order the processing of these tasks is going to influence the performance of the system. It's going to influence the interactivity, what the user experiences, and how efficiently the system might run. So if you recall, since we're focusing on CPU scheduling, let's remember what the thread abstraction can be in. It's in multiple states, right? When a thread is first created, it's in the new state, and it enters the ready state to be executed. When the scheduler decides to run a thread, it'll enter the running state, and an interrupt will take it back to the ready state. If the thread tries to execute an I/O or some other operation that causes it to wait on the operation to complete, it'll enter the waiting state. And once that operation's completed, usually it'll re-enter the ready state. If the thread exits or crashes, the thread's going to go from the running state typically to a terminated state. This should look like the process states that we saw in the early lectures, just a little bit simplified. Why do we care about scheduling? Well, it comes back to what are the goals for our scheduling algorithm and what are we going to see as a user or developer as a result of those? At a high level, there are three main goals. The first is throughput, the number of processes we can complete in a given amount of time. We'd like to complete more processes. Then there's the turnaround time. This is the time for each process to complete. The lower, obviously, is going to be better here. And often we'll look at the average turnaround time, the average time that it took for all the processes to complete given a set of tasks that we tried to execute. And then third, we'll look at the response time. This is the time from the request to the first response. So think about when you're using your computer and you click with the mouse or you press a key, you'd like your computer to feel responsive and to immediately process that request. The lower the response time, the better. All of these above criteria are also going to be affected by secondary criteria. How efficiently we use the hardware. If we have 4 cores, how efficiently can we keep all the cores actually in use throughout the execution? And the waiting time. How much time is the processes spending in the ready queue? This relates, again, to response times. In addition to this, there might be other criteria for specialized scheduling, thinking about power management or latency. These other kinds of factors are something that more advanced schedulers might also look at. So this brings us to the first scheduling algorithm. And like we've done with other parts of the lecture, we're going to look at a few high-level scheduling algorithms that are still in use in various parts of the system, but they might not be often used for CPU scheduling today, and see how they perform to understand these sort of building blocks that are used to build these higher level or more sophisticated schedulers. And toward the end of lecture, we'll look at 2 real-world schedulers that are in use today. The first policy that we're looking at is the first come, first serve policy. So this is pretty straightforward. If I get tasks P1, P2, and P3 in that order, I'm just going to process them in the order that I've received them. Here, let's assume that P1 needs 24 seconds, P2 and 3 need 3 seconds to complete. So this is a really easy scheduler to implement. So let's look at these parameters that we looked at in the last slide. The throughput. Well, in 30 seconds, I'm going to complete 3 jobs. So it's roughly 0.1 jobs per second. And the turnaround time. So we have these 3 processes. They completed at 24, 27, and 30-second boundaries. The average turnaround time is the average of those 3, which is going to be 27 seconds. So can we do better? Well, of course. If we just reorder the order that we process these things, if we process P2 and P3 first and then P1, well, what happens to the throughput? The throughput doesn't change, but the turnaround time now is much shorter. The average turnaround time now is only 13 seconds compared to 27 seconds previously. The lesson here is that the scheduling algorithm can reduce the turnaround time. We can minimize the waiting time. One of the important ideas of scheduling is that we're not using a single resource all the time. It's not just that programs are only using the CPU. Conceptually, the program's using the CPU and I/O. The I/O could be the disk, the network, multiple disks, all these different resources that it might be waiting on. It might be locks, it might be other things. What we'd like to do is maximize the throughput of the entire system, keep all of the CPUs busy and all the I/O devices busy. And we do this by overlapping I/O and computation across multiple jobs or multiple threads. One thread will be doing computation using the CPU, while another thread might be busy doing I/O. So it's in the waiting state, waiting for that I/O to complete in the background. When the thread that's using the CPU is done with its use and it starts issuing a new I/O request, then the other thread could be scheduled to process the I/O request that just completed. And hopefully by having lots of different threads in the system, we can overlap and maximize the use of the CPU and all of the I/O devices at all times. One of the insights that's going to help us with making scheduling decisions is realizing that for most programs, they have really short bursts of CPU. They use the CPU for a few milliseconds. Then they release the CPU in order to complete some I/O request. So here we're showing a diagram of basically CPU burst times, how much CPU is used between I/O requests for a given application, and the frequency that those different I/O requests are used. And what we can see is that while we have a long tail of very long CPU tasks, most CPU tasks are incredibly short-lived. They're just a few milliseconds, and then an I/O request or operation is going to be done that's going to require us to place the thread in a waiting state while other threads can run. So let's put these two things together to see what happens when we mix a CPU-bound job and an I/O-bound job. We're going to assume that the CPU-bound job is going to hold the CPU basically until it exits, or it does an I/O, but those I/Os are going to be very rare, while the I/O-bound job is going to mostly be doing I/O and doing small computations in between. If we were to mix these two tasks on the same system, on the same core, using a first-come, first-served scheduler, we would see that the CPU-bound job would run for a while, and the I/O device would be idle, and the CPU-bound job then suddenly blocks. Maybe it needs to do a small I/O or something, and then the I/O-bound job gets an opportunity to run, and it's going to quickly block because it's almost immediately going to issue an I/O. As soon as the CPU-bound job starts to run again, it's going to run. The I/O might have completed in the background, but the CPU-bound job will just continue to run, starving the I/O-bound task. And this is known as the convoy effect. We have these large tasks, the CPU-bound tasks, that are basically holding all the other tasks in the system up with this first-come, first-served scheduling policy. And what's happening here is if you can think of the I/O device as basically another core in your system. It's a resource you care about using, and you're starving that resource because you're prioritizing the CPU-bound task using this scheduling policy. The shortest job first scheduling policy attempts to minimize the turnaround time. This is one of the solutions to the problem we just saw. The idea here is that we'd like to schedule the job with the shortest CPU burst first. We could do this with a non-preemptive or a preemptive scheme. The non-preemptive scheme, if we knew the lengths of all these different tasks, we would run the shortest task first. In the preemptive scheme, which is what you'll see sort of similar to scheduling policies you'll see on modern computers, what we'll do is we'll give every task some amount of time to execute, and we'll try to run the task with the shortest remaining time. And if a different task has a shorter time, we'll try to preempt and give that to another task. What does this scheduling policy actually optimize? Well, it actually minimizes the average waiting time for a given set of processes. So let's look at a couple examples here. So we have on top a table, process 1, 2, 3, and 4. They arrived at different times, 0, 2, 4, and 5. And we know the rough burst time for each of these processes. In a non-preemptive scheme, we would first start off by running P1 because there's no other task to run at that time. By the time P1 completes, we're already at time 7. We now have seen all 3 other processes and we know how long they're going to take. So we'll prioritize P3 and then we'll run P2 and 4. In the preemptive scheme, we'll run P1 for 2 units of time, but we'll then preempt the process as soon as P2 arrives because P2 is shorter. And the same thing will occur when P3 arrives, and then we'll give the CPU back to P2, and then back to P4, and to P1. As you see, in all these cases, it still takes us 16 units of time to complete all these tasks. All we've done is just change the turnaround time. So, what are the drawbacks and limitations of the shortest job first scheduling policy? The main one is that it doesn't always minimize the average turnaround time. It only minimizes the waiting time, which minimizes the response time. The shortest job first scheduling policy can lead to unfairness and starvation. We didn't really mention this before, but one of the things we like with scheduling policies is usually to have some form of fairness. That is, we'd like to run all the processes a little bit to make sure we're constantly making forward progress and we're keeping things very responsive. In this case, we might be starving long tasks in favor of lots of short ones and not allowing the long tasks to complete. In practice, the bigger problem is that what we presented here requires us to have an understanding of the future execution of a program. We don't really know for sure how long the CPU bursts are going to be. We can estimate the CPU burst based on past behavior and then use some kind of smoothing to allow us to continue to estimate as the program evolves what we think the next CPU burst will be, but there's no real guarantee that those parameters will be maintained. In fact, if you recall in some of the previous lectures, we talked about how programs can have these phase changes. They might be CPU bound for a period of time and then behave like an IO bound tasks at other times. It could be that some threads of a program are CPU bound and other threads are IO bound. The round-robin scheduling policy is another simple policy that gives us a different set of trade-offs. Here, we're focusing on fairness and starvation. We're just taking all of the programs in the system and we're going to run them in a round-robin fashion. So if you have 3 programs, A, B, and C, we're going to run A, B, and C in a round-robin fashion, give each one a fixed amount of time, a time slice, or sometimes referred to as a quantum, to execute, and then we'll preempt the program and allow a different one to run, and we'll just run them in a FIFO queue, a first in, first out queue. most systems are actually going to do something similar to this and to a shortest job first scheduling policy we'll see in more advanced algorithms toward the end of this lecture. The advantage here is that we'll get a fair allocation of CPU across all the jobs. We'll have a low average waiting time, and it's just really going to vary based on the job length. And we're going to have good responsiveness if we have a small number of jobs. What's the disadvantage? Well, there's a few disadvantages. What if all jobs are the same size? Assume you have 2 jobs and they take 100 units of time each. Well, if context switches were free, the round robin policy will perform the same as a first come first serve policy. But if context switching between these threads or processes isn't free, which we know it isn't, we discussed how this is costly in several lectures, then this policy is going to take some amount of time longer to run than a normal first come first serve policy. This brings us to a few issues that we should consider before we get to looking at more real-world scheduling algorithms. The first is the context switch cost. As time progresses when a program is running, the cache is going to be loaded with memory that belongs to that individual thread or process. The same is true for a tag TLB for the virtual memory hardware. Both of these things add to the context switch costs when you're switching between processes or when you're moving processes between cores on a multi-core system. We need to consider all of these effects when we're deciding what our quantum is. So at a high level, remember that the scheduler, when we use a preemptive scheduler, which most modern operating systems use preemptive schedulers, we need to select a unit of time on which we're going to interrupt the program and run a different program. We need to select a unit of time that we're going to interrupt a program at, or a thread, to run different threads. And the way we select this is that we want to make sure that the context switch cost is going to be reasonable given the quantum. So we want the time that's spent in the quantum should be much greater than the context switch cost, so we can hopefully minimize that cost through the execution of the thread throughout that quantum. That is, the thread at the very immediate run might start filling its cache and warming up its cache and its TLB, and by the end of its quantum, it should be running at nearly full speed again, as if it ran continuously for the entire duration of the program. We want to make sure that the majority of the bursts are also less than the quantum. Otherwise, we're basically going to revert most scheduling policies to either a first come first serve or a round robin policy if we don't have a nice way to visualize what the program's doing. So the typical values that you'll find in most schedulers are anywhere from about 1 millisecond to 100 milliseconds. So to give you a few data points, typically in servers, they'll be on the longer end of this in tens of milliseconds. Hypervisors, the virtual machine monitors, because the context switches are so expensive, are often scheduling on the order of 100 millisecond runs, 100 millisecond quantums. And more interactive systems like desktop OSs sometimes go as low as 1 millisecond to make things more responsive to the user. Another issue that's common in schedulers is that we'd like a way to have priorities. In most Unix operating systems, we typically have numeric priorities that are associated with each process. This way, we'd like to prioritize higher priority tasks, or sometimes even real-time tasks, over low priority tasks that are running in the background or batch processing tasks that might just be doing computation that we're willing to wait a long amount of time. If you think about it, the shortest job first scheduling policy is basically a priority scheme that's predicted based on the CPU burst time. The shortest job first policy basically runs shorter tasks, interactive tasks effectively, because it sees tasks that have short bursts of computation and lots of I/O as interactive and real-time tasks that are going to run more frequently. Longer running CPU-bound tasks naturally are more likely to be batch processing tasks. Many scheduling policies usually are going to combine these factors together. They're going to use something like a shortest job first policy that's influenced by the priority system and combine that with a round robin policy within each priority level. The problem with this idea is that there can be starvation. It might be the case that a low priority process would never execute if a higher priority process is always ready to run. So what's the solution? Well, the solution is some form of aging. We either increase temporarily a process's priority as it waits. So the longer a process hasn't run, we keep boosting its priority every so often. And then that way it always has a chance to run, giving some form of fairness, or decreasing the priority of tasks that are running their entire quantum and not allowing other tasks below them to run. Sometimes both of these can be combined. So this is going to bring us to the first real-world scheduler that we're going to consider. This is the multi-level feedback queue. This is the original scheduler that was implemented in the BSD operating system. Many schedulers follow one of several types, and we're covering the two main types that make up most OS schedulers today. In the multi-level feedback queue scheduler, what we have is 128 priority levels, and within those, we've grouped them into groups of 32 separate queues. And what we try to do is run the process with the highest queue from the highest priority queue. So here you can see there's a yellow task at 0, and at 4 through 7, this is the highest priority, and priority levels 4 through 7 have a lower level priority tasks, and there's a bunch of them, there's 6 of them there, and below that there's that purple task at 8 through 11. And what we're going to try to do is try to run the tasks that are at the highest priority levels. So starting with 0 and working our way down, running each non-empty queue in a round-robin fashion. While many schedulers are based on the idea of the multi-level feedback queue, we're going to use the formulas from the BSD scheduler to better understand what's happening here. Remember, the key idea of the way the scheduler works is it's going to look at the highest priority queue that is not empty and run the programs in that queue in a round-robin fashion. In between all these things, we're going to constantly be recomputing the priorities of all of the programs in the system. There's two parameters that matter here. The first is the nice value. This is a user settable waiting factor. It's the user settable priority for the process. If you want to make a program run more, you can lower its priority by giving a negative nice value. And if you want to run less, if you want to lower it, you can decrease its priority by making the number larger or more positive. The second is the estimated CPU. This is the per process estimated CPU usage. Remember that in this version of the multi-level feedback queue, the lower number refers to a higher priority. And the way that it works is as a program is running, if we deschedule the program because a timer interrupt triggered, what we're going to do is we're going to just increment the estimated CPU. We're making the estimated CPU a little bit larger. And what this is doing is this is effectively decreasing the priority of the program. When the program is runnable but not actually running, every second, we're going to decay its estimated CPU. So we take the estimated CPU, we're going to multiply it by this load factor. The load factor just adjusts how fast the decay occurs based on the length of the run queue. And we're going to add the nice value. And then we use this estimated CPU value to compute the priority queue that the process should be in. We take 50, so we're somewhere in the middle of the run queue. Remember that the run queue is clipped at 127. We then take the estimated CPU over 4 and we add twice the nice value. When you compute this, what's happening when you combine these two things together? Well, when a program's running, the estimated CPU is slowly decreasing its priority, giving more chances that other programs can run. When a program is runnable but not actually running, we slowly decay its estimated CPU usage so that it has a better chance to run, trying to boost the chances that we pick it and move it to a higher and higher priority queue. The second thing that we do is when a program is asleep, what we do is we keep track of the sleep time. And as soon as it becomes runnable, we're going to adjust the estimated CPU, again with the load factor, to the power of sleep time times the estimated CPU. Again, what we're doing is we're basically decaying the process's estimated CPU for how long it hasn't been running, but we've ignored the nice value in this case. If you want to see the full description of the scheduler and see more detail into each of these algorithms, the design and implementation of the 4.4 BSD operating system goes into depth in this scheduler, and also the same author, Mikusic, which we'll talk about more in the file system lectures, has also written books on newer versions of FreeBSD that also touch on the original 4.4 BSD scheduler. Remember that we mentioned when we look at context switches, there are a couple different things that can play out here. One is when we're switching between different programs on the same CPU, or we're switching programs between CPUs. They both come with some kind of cost. In a multiprocessor system, we need to decide on which process to run on which CPU. And we know that moving between CPUs has a cost. It's larger than a context switch cost in some cases because of the cache misses and the TLB misses. So we have a few choices. We can have some kind of affinity where, we can either have a single scheduler that assigns programs to all the CPUs, or we can make individual scheduling decisions per CPU and then deal with load imbalances at a second level, looking across all the CPUs and trying to rebalance applications. Another interesting aspect here is dependencies between threads or processes. So most schedulers deal with this thing called priority inversion or priority donation, which occurs with locks. Remember back to the locking lecture, we can have multiple threads grab different resources that could be held by locks or other resources, and those threads could have different priorities. When we combine priorities in locking, we can run into some kind of starvation issues. So here, imagine that a low priority process acquires a lock, and then a high priority process tries to acquire the same lock. It fails and it's spinning, but it never lets the low priority process run. Another way that this could play out is you could also have the high priority process try to acquire the same lock. It fails, it blocks. A medium priority process runs in the system and doesn't let the low priority process to run. All of these cases are examples of priority inversion. A case where a high priority process is effectively starved because of some interaction preventing a low priority process to release a resource that it's holding. Scheduling decisions should deal with this. So the way that most schedulers deal with this is with some form of priority donation. In addition to the priorities that we saw in BSD, we can adjust the priorities to deal with lock dependencies between threads or between processes even. An example here, we have a low, medium, and high priority task. The low priority task holds lock L. The medium wants L. So what happens? Well, what we do is we donate the priority from the medium task to the low priority task. So the low priority task temporarily receives the maximum priority of all tasks waiting on the same locks that it's holding. So in this case, we'd boost its priority to a medium level priority. The high priority task is also waiting on the same resource now. And again, we'll do the same thing. We'll just boost the priority of any low priority task to a high priority to ensure that it gets to run until it releases the resource and will be reduced back to a low priority task. We can think of multiple different schemes where this happens. And in every case, the solution is to basically take the maximum of all priority levels that are waiting on a lock or any other resource and donate that to the tasks that are currently holding that resource. Once that resource has been released, then this can be given back. So this brings us to a second class of schedulers that are very common, that are based on the notion of virtual time. The borrowed virtual time scheduler is the example we're going to use today, but there are many versions of this, and they all look very similar to the BVT scheduler, including the Linux CFS scheduler, which is the default scheduler in Linux. The idea here is a lot simpler. We just want to run the process with the lowest effective virtual time. And for every process, we're going to keep a notion of the actual virtual time consumed by that process. And we're going to denote that by AI. In the case of BVT, it supports the real-time applications through this warp mechanism. And to do this, we'll actually use the effective virtual time for all virtual time scheduling decisions. And here we represent the variable EI, which is just the actual virtual time AI of a given process minus its warp. Real-time applications will have some warp factor, WI, capital WI, and they'll have a flag, the warp flag, that decides whether or not the real-time priority is still given to that application. And what the purpose of this real-time, and we'll see this in a couple slides when we look at a real-time example, is that it allows an application to temporarily violate fairness and borrow against its future CPU time in order to make it more responsive in the short run. So this will be great for media applications and games and things like this. In the BVT scheduler, every process is going to get a fraction of the CPU determined by its weighting factor. Every process is going to have a weight, lowercase wi. This is not related to the warp, the capital W. So here, a process I should receive its lowercase wi over the sum of all the weights in the system. This is just a fraction of the weight given to that process. Other schedulers might refer to this weighting factor as shares or tickets, as we'll see in the lottery scheduler, which you're going to do in your reading, and we're going to touch on in the last slide of this lecture. The way we can think about this in the case of the BVT scheduler is that WI seconds of execution are going to be done for every virtual time tick for a given process I. When I consumes T CPU time, what we're doing is we're tracking it by taking AI and adding T, the time consumed, divided by the weighting factor. So here, in this example, we have GCC and BigSim that we're going to use throughout the remaining examples. And GCC has a weight of 2 and BigSim has a weight of 1. This means that GCC is going to run twice as long as BigSim. So if we assume there's no I/O, we're going to run GCC for 2 units of time, then we're going to run BigSim, then we're going to run GCC for 2 more units of time, and then BigSim, and so forth. This tends to lead to a lot of context switches, so it's not good for us to just assume that as soon as another process has a lower virtual time, we should immediately switch. To mitigate this and to reduce the number of context switches, the BVT scheduler has a notion of a context switch allowance, which is denoted by C. Here, all it is that we're only going to switch to another process once we've exceeded the virtual time by this C factor. And C is in wall clock units, so we have to divide it by the weight as well when you use the formula shown in the slide. So here we can see a simple example of GCC and BigSim as we described earlier, running, and real time on the x-axis and virtual time on the y-axis. Every time virtual time is increasing, we know that the process is running. And if we look in the steady state, BigSim runs for here, C was 2, so BigSim ran for a period of time until it exceeded that C factor, and then GCC ran. And you see that GCC runs approximately twice as much wall clock time as BigSim. It's increasing at twice the rate. BigSim is consuming twice the rate of virtual time. All the processes' virtual times are lining up roughly, but the wall clock times are not the same because of those weighting factors. So this is simple when we think about processes that are only executing CPU all the time. We haven't considered what happens when a process goes to sleep. When a process sleeps, with the BVT scheduler up to what we've described till now, the virtual time of the process that slept will be far behind all of the other processes in the system that are continuing to execute. This means that programs that sleep for a long period of time can wake up and then starve everybody and just consume the CPU until they've caught up with everybody else's execution. And this really isn't fair. So the BVT scheduler bounds how far behind a process can be when it wakes up with this notion of the scheduler virtual time. This is a global minimum of virtual time for all currently runnable threads. And all we do is that we monitor all the currently running or runnable threads, and we take their minimum virtual time and we use that as the scheduler virtual time. When we wake up a program that was voluntarily put to sleep, that program will then be assigned an actual virtual time of its previous actual virtual time and the scheduler virtual time, taking the max of those two. Note here that we are making a distinction between voluntary and involuntary sleeps. We don't reset the virtual time when a program takes a page fault, because we're basically giving the opportunity for that program to catch up from involuntary sleeps. But voluntary sleeps, when they're sleeping because they've chosen to go to sleep for a period of time, or they're doing I/O, should be reset in this manner. So here we're showing GCC and BigSim again with the same weighting factors, and if you look at the top right of the graph, it should look similar to before, but the difference is for the first 15 units of virtual time, of real time, GCC was asleep and then woke up. During this time, there were no other processes, so BigSim consumed the CPU entirely, and at time t = 15, GCC wakes up, and we can show both opportunities of what could happen. In the blue line, we show what happens if we just woke up GCC with its initial virtual time that it has. And we'll see that its actual virtual time fell far behind BigSim, and in that case, it's just going to consume CPU until it's caught up. So it might run for a long amount of time, starving all the other processes in the system. So the BVT scheduler obviously resets the actual time of GCC to the scheduler virtual time, which in this case, because there's only one process, it'll be the same virtual time as BigSim. So at time equals 15, we reset it to the virtual time of BigSim because it's the only other process, so that's the minimum for the entire system. And we continue making our scheduling decisions. This way, GCC doesn't get some unfair advantage because it slept for 15 seconds, and the processes continue to obey their waits once GCC wakes up. So let's look at one last thing with the BVT scheduler, which is see how that warp factor and the warp flag work. Basically, the idea here is that we want to be able to support soft real-time threads, and virtually every desktop OS has some notion of this to support games, video, music, or any kind of processing that has to be done roughly to some deadline. Here, we can recall the flag, what we use for all the computations is the effective virtual time, EI, which is just the actual virtual time minus the warp factor if the warp is enabled, or 0 otherwise. And the warp factor just gives us an amount of room that a task can run whenever it needs to in order to satisfy its real-time needs. If it exceeds that factor by some amount, then that task will be penalized by disabling its warp and returning it back to a normal task. Over time, that penalty will be reset. So here, let's just look at a simple example when the warp flag is working and set. And we have 3 processes. We have the GCC BigSim, which should be executing still in their 2-to-1 ratio. And we've introduced the MPEG task. And MPEG is a video encoding task that's running in the background, and it's a real-time task, so it needs to constantly run to process a frame every so often. So we can see at time t equal 5, the MPEG task woke up, and you can see this vertical jump here because we reset the actual virtual time of the MPEG task to be the scheduler virtual time, which is coming off of the GCC line above. And then we subtracted 50 for its warp value. So the program started up because it had the lowest virtual time thanks to its warp. It executed for a short period of time, and then it went back to sleep. And then GCC and BigSim are consuming CPU at this point, and then the same thing happens again. Again, at time t equal 15, MPEG wakes up again. Its virtual time is far behind everybody else. We need to reset it to the scheduler virtual time. So we take again the lowest of the remaining running tasks, which is GCC, and we reset the actual virtual time of the MPEG. And then again, remember that we're showing here the effective virtual time, so we subtract 50 again for the warp value, and the MPEG program runs for a little bit, and then again it relinquishes the CPU, allowing GCC and BigSim to continue running. The nice thing here is this MPEG player, it's acting as a real-time task. It's processing a frame of video, it sleeps for a period of time, and then it wakes up to process another frame of video, and it's given this high priority thanks to the warp value, so it's able to immediately process that frame and then return control of the CPU back to other tasks. This way, it's not going to miss any frame, and it's going to continue to be able to meet the deadlines for the video processing as long as the system overall is not exhausted with real-time tasks. So let's see what happens when this breaks down. So if the MPEG player, for whatever reason, ran too long, and we assume that the LI, the limit flag, is 10, and somehow warp gets set to false at time t equal 10, well, what happens? Well, we disable the warp, which basically jumps the MPEG player back to its normal virtual time. And you see that vertical jump there when it's set to false. And then the MPEG will just run like any other process in the system. And this will occur until at some point in the future that this penalty will be removed based on the algorithm in the scheduler, which we won't get into. But you can see the original reference from the first slide about the BBT scheduler to see all the details. I should note now that the warp flag and the warp factor are not the way that Linux implements real-time scheduling with the Linux CFS scheduler. While the Linux CFS scheduler looks a lot like BBT, the real-time handling is actually handled by separate queues independent of the Linux CFS scheduler. So one last thing we're going to touch on, which is the lottery scheduler. The lottery scheduler is the scheduler you're going to read about for your first reading assignment, and it's a very simple scheduling strategy, and it shares a lot with the virtual time schedulers once you understand it well. The basic idea here is that at every quantum, we're going to run a lottery and randomly choose a process to run. That's it. Each process can have a priority based on assigning it a number of tickets in the lottery. So just like any other lottery, any process can have one or many tickets, and we'll randomly choose a ticket, and that'll correspond to one of the processes in the system. So processes with more tickets should run more frequently than processes with fewer tickets. The tickets are sometimes referred to as shares, or in the BVT scheduler, they're referred to as a wait. They're all going to perform similarly, and it's going to have similar behaviors to the BVT scheduler.